I guess my iPad's the host. All right. Questions about anything before we get started with some notes? So we're going to do a little bit of notes at the start. We'll do the quiz at the end. I don't think I had anything else I really wanted to say. Are there questions at all? Anything you want to talk about? All right. Let's do this. Come on. Oh boy. That seems good. All right. So we were looking at continuity last time. And as a quick reminder, this, we're using our concept of limits here to talk about continuity. So it's what's inside the red box. I'm just going to kind of underline it again in green there. But what it's saying is if we have a continuous function at a specific point, so we're talking about the specific point C, well, it means what we think it means, right? So you can trace your function and you don't take your finger off the page at that point is kind of what you should think about. But when we think about like the precise mathematical definition of what that means the limit exists at that point, which means you're approaching the same place from both sides. And the function value is defined there and it equals the limit, right? And so in this first example, we just did like a very simple example with the picture here with the hole in it, right? We had, and we're talking about this point right here, obviously, right? We're talking about the point with the hole. When you approach that point from both sides, like the left-hand limit, the left-hand limit and the right-hand limit are both approaching that same location, but the function value doesn't exist, right? And so we just said that this is not continuous at that point because of that very reason, right? We went through each one of those things, 1, 2, 3, and we said, well, the limit exists, the function value is not defined, and so since the function value is not defined, it's not continuous, right? So we're just kind of like carefully thinking about when these conditions do or don't fail. And we're going to jump right in and look at some actual functions today that we're starting with. So with it, but I just wanted to start with that, just remind you where we were. Are there questions about this example that we left off with last time? I'm going to clarify there. So the homework next week is looking at these kind of problems. Like, where is this continuous? It'll either be a graph or a function, very much like this page. So 1 over x is a function that we've seen a couple times already. And we've seen the graph of it as well. And so I'm just going to start by graphing that. Right, we know 1 over x does this. That's what the function 1 over x looks like. And it has a vertical asymptote at 0, at x equals 0, right? So it doesn't, these lines are getting closer and closer to this red dotted line, but it's never touching that. And there's an asymptote because you can't plug in 0, right? There's an x in the bottom, so you can't plug 0 into the bottom. That's what makes the asymptote. And so the question is, if we wanted to think about where is this function continuous, right? So back up to these 3 conditions. We're thinking, where does the limit exist? Where is the function defined? Where does the limit equal the function? Where does the limit equal the function values? And so it's going to be everywhere on this graph except at 0. Right? If I'm tracing out, if I just kind of zoom in here, if I trace this graph out along here, this is all one continuous thing, and it just keeps going this way, and I don't have to lift my pen off the page, right? Same thing with the other one. This is all continuous. The problem is when you jump from this piece to the other piece, you lift your finger off the page, and that's where the point is not continuous, right? So there's some issue at 0, in other words. And what is the issue? So out of those 3 conditions, what's the issue? At 0, at x equals 0. Does the limit exist? Is the function defined there? Does the limit equal the function value? Thoughts at 0 in that graph? So something fails at 0, at least one thing. That's what that is. Yeah. Yeah, so this undefined, so number 3 automatically fails at 0. What about the other conditions? Does the limit exist at 0? No, why not? Like, what's the issue there? Do you know? What's the, yeah. You divide by 0. So I guess what I'm wondering is, when we looked at places that limits don't exist, so let's go up to that real quick. Places that limits don't exist, that was one of the first pages. Oh shoot, we didn't. That's right, it's before we did this. But it was this example that we're looking at here. It's actually almost the same thing, right? So this one was ended up being, it's called a infinite discontinuity. So if you happen to look back on page 4, you should have a nice picture of an infinite discontinuity right there. And so that's what's going on in this one. It's almost the same function actually. It's a 1 over x thing, right? And so the problem is that the left and the right hand limit don't exist because there's that infinite discontinuity there. So let's just carefully write a few of those things down. So out of the conditions on the top there, 1, 2, and 3, they're actually all met everywhere except 0. I want to just be clear about that. So they're met everywhere except at x equals 0. Right, at x equals 0, that's where you do the jump thing with your finger on the page. And so something weird is happening at x equals 0. And as you guys just mentioned, it's the function's not defined there. So number 2 fails. Is that what number 2 was? Number 2 fails, and number 1 fails. And so since number 1 and 2 fail, number 3 also fail because they can equal each other, right? So at 0, all 3 conditions fail is what I'm trying to say. Okay, so except at x equals 0, at x equals 0, f of 0 is undefined. Oops, forgot the m there. And the limit doesn't exist. And more specifically, it's because there's an infinite discontinuity. If you want to look back on page 4, you should have that in your notes. Discontinuity. And so this one's a real mess at 0, right? Like it's just looking at the picture, it's very clearly not continuous at 0. And we're saying, well, not only is it not defined, but the limit doesn't even exist. And so all these things fail, right? So all 3 fail. So all 3 conditions fail specifically and only at x equals 0. We're just trying to carefully apply these definitions right now. And each one's going to be a little bit different. Looking at pictures is a really nice way to sort of confirm what you're thinking. And as I'm emailing with some of you guys about the homework on Wednesday, we have these ways to evaluate these limits by hand without using calculators and looking at pictures. But it's nice to look at a picture, just be like, is what I'm getting by hand correct? Or if you get stuck, looking at a picture like that can be really helpful, right? If we did this problem without looking at the picture, it becomes much more challenging to think about, right? All right. Questions? Questions about that at all? Let me break this page up a tad bit. Questions? Anyone remote here? Let's see. Hold on a second. Someone's trying to say something. Maybe let me try this. Someone trying to talk remotely? Try it again. I've got the chat open on this computer. Yeah, that's an old thing. Janetta, were you trying to say something? Looked like your screen was highlighted, but my thing was muted. Let me make sure my speakers are on.
No.
Okay. Let's look at the square root one. And again, let's just draw a picture. And it's kind of a funny one because it's got a square inside a square root. And so that creates kind of a funky picture, actually. And maybe I actually want to delete that one. Yeah. Actually edit that one too. Great. So let's draw the picture. So if we drew this picture, it ends up looking like a half circle. It does this kind of thing. And it goes between -1 and 1. Right, if you plug numbers bigger than 1 in there, then you do 1 minus them, and it becomes a negative inside a square root. And so it's only defined between -1 and 1. So that's how you could draw a picture of a half circle. And if you did plus or minus that, that would complete the circle. Anyway, we're talking about continuity though. This is a very continuous function on its domain, right? If I trace this out, if I just kind of trace out with my pen here, I don't lift up the pen at all anywhere between those 2 points. And so anywhere between -1 and 1, I hope you'll agree, is continuous, right? So mathematically speaking, if we approach any point on this function, it will exist, and the function value is defined everywhere. And it equals the function value everywhere, actually. And so that's for every c between -1 and 1. And notice how you think back to your pre-calc folks who had me at least, right? Do we have parentheses around the 1? So we're not actually including the 1s, right? Because something happens at the endpoints. Even though you might think it's continuous at -1 and 1, I'm going to argue that it's not continuous at the endpoints. Thoughts about that? Why do you think it's not continuous at the endpoint?
Because they minus each other.
So 1 is positive and 1 is negative. That's absolutely, so someone in the chat, I don't know if you guys could hear that. Maybe I should connect this. Anyway, I should connect this over here. Do I want to do that? Okay, echo, no, I won't. Anyway, that's a good thought. So they are negative each other, but when we're thinking about that, that doesn't really tell us something about one of these 3 conditions, right? And this middle condition is fine, check. The function value is defined at those places. So it's something about the limit. What about the limit is weird at the endpoints? It doesn't exist, but why? Yeah, like, right, so if you approach the -1 from the left, it's going down towards there, right? But you can't approach it from the other side. There's no graph over there to approach it from. Same thing on the other way, right? Yeah, the right-hand limit exists over here, but there's no, I'm sorry, the left-hand limit exists over there, but there's no right-hand limit. So it's kind of, you know, it's not that the function's not defined there. I want to be really, really clear. Those are filled in circles. F of -1 is 0. That exists. It's just that the left-hand limit doesn't exist there, so you can't meet these requirements for continuity. It's like a kind of a, I don't want to say a special case, but it's carefully using the definition, right? And so however, it's continuous everywhere, but if we try to approach -1 from the left, it doesn't exist. And if we try to approach +1 from the right, it doesn't exist. So it's technically not continuous at those points. The other way to kind of think about it is you can't like move through those points if you were trying to trace it out, trace with your finger, right? You kind of like hit a wall there, and so it's the end of continuity in some sense. In other words, condition 1 fails at x equals -1 and 1. And so we would say this function is continuous on the interval, the open interval -1 to 1. Right, so kind of final takeaway then. So just to be very clear, I'm hoping people from my pre-calc class remember this, but when you put a parenthesis around a number, it means you don't include it in that interval. I'm just trying to be very clear about that here. Right? Yeah, thank you. Yeah, so So a bracket, so I don't know how to slip this in. Including it would be like a bracket. That would be include. But when you put a parenthesis on there, it means you don't include it. I don't want to leave that hanging there, though. I'm afraid that someone might look at this later and think that's confusing. So I'm going to erase that in a second. But yeah, that's the difference, right? Parentheses versus brackets. So just a notation thing, but it's an important notation thing. It's kind of like, I always try to relate this back to English, right? It's like using the right punctuation and things like that when you're writing a sentence. It just confuses what you're trying to say if you don't use the right punctuation. All right. So I'm going to erase that part. Thoughts about that idea? All right, the last one on this page is one we've also seen before, although again, it's the one that we saw before I started using my iPad. And so sine of 1 over x, if you remember, it does that weird oscillating thing. So if we kind of graph sine of 1 over x, it looks like sine, but as you get closer to 0, the oscillations get closer together. And when you get really close to 0, they just like bounce back and forth like crazy. And then when you move away from it, they start to spread out again.
That wouldn't have a limit.
Yeah, exactly. So we saw this example. Thank you for jumping in on that. We saw this example back in cases when limits don't exist. So again, back on the page that's currently blank on my iPad, we said that the limit is, even though it's sort of continuous there in the sense that you can lift your, you keep your finger on it, but it gets so crazy around 0, it's not actually approaching something as you get close to 0. It's literally just like bouncing back and forth like crazy. And you can't actually plug 0 in anyway, because you have 1 over x in there, right? So you have like undefined inside there. So it actually like jumps over 0. It gets like really, really crazy around 0, and then it jumps right over it. In fact, let's just go ahead and look at that. I've been meaning to graph this for you guys, so we might as well just go ahead and graph it. And I also wanted to just show you what this great website, if you've never used it, it's a good way to check answers, look at graphs. I always come here if I want to look at a quick graph. And you can just like type in English what you want. So I'm gonna like, let's graph this near x equals 0. And it'll come up with a nice picture for us. Now you can get really great stuff if you pay money. And so sometimes I try to do something and it doesn't work, but you can just see, right, it's like crazy right around 0, and it just like becomes like a solid line. And it's the kind of thing where if I paid money and got an advanced version of this, you could keep zooming in closer and closer to that, and you would just have, like, there's no end to the number of lines that would there be, right? There's infinitely many lines just bouncing back and forth near 0. Because you're almost dividing by 0. So it's like, I'm getting really close to dividing by 0, and it starts freaking out and going back and forth. In some sense, one way to think about it. So just driving home what we just said then, the limit doesn't exist, and the function is not defined there. So it's a similar situation to the one above it, but a different kind of graph, right? So that's one of the reasons I wanted to look at this. So the final takeaway here is, if we try to approach any value here, it's fine. That's going to happen everywhere except x equals 0. And so taking that a little bit further, at x equals 0, the limit doesn't exist due to oscillations. And moreover, just to make it even more clear, sine of 1 over 0 doesn't exist either. And so all conditions fail. Sorry, it's getting kind of cramped there. Maybe in a future class, I'll put that in its own page. This word right here says conditions. Maybe I can make that better. Okay. Now we just did all that using pictures, but we can also do it using limits, because we know how to use limits as well, right? We could plug numbers in near the point or if it was a rational function, maybe we would use the conjugate technique, things like that. But there's ways we could approach this by hand as well. I'm trying to do it just with pictures, and I think most of the homework does that as well. Although there are a couple questions related to, I think, piecewise functions. And what I usually like to do is let people just kind of look at the homework a little bit, and then we can do some in class. So anyway, maybe over the weekend, just take a look at those, and then Monday or Wednesday, we can do some of the confusing ones. Yeah. Yeah, so can I do this? I'll kind of go onto this page and write that down. So sine of 1 over x, it's continuous everywhere except 0, right? So it would be the same thing for actually 1 over x as well. So it would be continuous on minus infinity to 0, union 0 to infinity. All right, so putting 0 in the middle there with parentheses, we're skipping over it. Yeah, good thought there. And so that also is for 1 over x for the same reason, right? They both have 1 over x in them, and so you can't plug 0 in. All right, good thought there. Other thoughts? I always try to think about how much of this next page I actually want to talk about, because it's not super important stuff, but so it's not super important in that like you don't see a bunch of questions on this, but it extends the ideas that we're talking about. So anyway, we're just going to look at it, and I'll maybe do a couple examples. What this is basically saying, let's just read what the definition says, is if we have two continuous functions, so they're called f and g, and they're continuous everywhere on some interval, right? Then the following functions are also continuous on the same interval. So it just basically says, if we have two continuous functions and we add them together or subtract them, if we multiply a continuous function by a constant, it stays continuous. If we multiply continuous functions together, they stay continuous. If you divide continuous functions, they stay continuous. So it's just saying all these different things that if you have a continuous function and you manipulate it a little bit in these specific ways, it'll still be continuous. With a few special caveats, right? So it's not like they're always going to be continuous, because there's things like this or this, for example, right? So there's like these added little conditions, same thing down here. This is actually not really conditions, just kind of clarifying it. But those two things there are actually conditions, right? So it's saying, hey, you can multiply or you can divide two functions. It'll still be continuous as long as the bottom part's never 0, because you don't want to divide by 0. So, so let me write down just a clarifying statement, and then I'll just show you an example of when this, like what we mean by that, right? So for example, not for example, what this is saying is when you add, subtract, multiply, or divide, or square root for that matter, or root continuous functions, they stay continuous. That's what this is saying. Except for a few conditions. Like the denominator not being 0, for example. Right, so the few conditions are like those couple things. So let's just do a couple examples. Oh, and the bottom one here says the same kind of thing, right? Is that what it says? It's just sort of telling us that most trig functions are continuous specifically on their domains. So I don't particularly find that, this is directly from the textbook, I don't find that to be particularly useful, because there are places, for example, where tangent is not continuous. And this is just saying, well, it's continuous at all the places that it's continuous. That is not very helpful. I think the first thing is a little more helpful. Let's dig into the theorem number 8 a little bit. So one thing that I've already mentioned that you should definitely keep in mind is that all polynomials are continuous everywhere. And so when someone says continuous everywhere, that means on minus infinity to infinity. Because they're not, there's, you don't divide by 0 in them, so you're not going to do like jumps or anything. There's no holes. You can just trace these out forever and ever in both directions, right? So for example, x squared plus 1, right? So U-shaped graph, there's no holes in it. You could just trace it out and it'll extend forever. That's a very simple one, right? Longer one might be something like this. A longer one, it's a quad, or as a cubic, it's got a cube in it, but it's still just a polynomial. Remember, polynomial means whole powered exponents, whole powered non-negative exponents. Okay. And what this, let's call this one F. Let me use a different color so it stands out a little bit. Let's call this one F, and let's call this one G. What the theorem at the top there says is F plus G is also continuous, because we're adding them together, right? So it's just saying like, hey, if you got two continuous things and you add them together, they're going to stay continuous. Very, very straightforward. Let's look at a quick example of one of the conditions. Yeah, I got a couple examples here. Some of them are good. Let me see which ones I want to think about. Yeah, let's do this right here. Let's explore this a little bit further. Let's let's just think about sine and x squared plus 1. One's a polynomial, one's a trig function that's continuous everywhere, right? Sine just like does the wavy thing forever, right? So both those things are continuous everywhere. So on minus infinity to infinity. You can plug any number into those. Another way to think about that is you can plug any number into those things and you won't get a problem on the calculator. What the theorem says is you can add them together, multiply, divide them, and they're also continuous, right? So the theorem's telling us that sine plus x squared plus 1 and sine times x squared plus 1, sine divided by x squared plus 1 are also continuous everywhere. Are also continuous everywhere. And we don't have to worry about anything in the denominator here, because that's never going to be 0, right? You can't, x squared plus 1 is never going to be 0. It's above the x-axis is one way to think about it. The other way to think about it is you're adding two positive things together, right? One is positive, and x squared is always going to be positive because you're squaring it. You're adding two positive things together, you're never going to get 0. So we don't have to worry about the denominator there. But if we did something like this, let's switch it around, x squared plus 1 over sine. Now we have to be careful about the denominator because sine is sometimes 0, right? But that thing is continuous everywhere except wherever sine is 0. So this is the condition, right? This is this condition right here that we're just trying to like be careful about. We're dividing two things and we're just trying to say like, well, is the bottom ever 0? Yeah, sine is 0. Does anyone want to bravely tell me where they recall sine being 0? Well, yeah, go ahead. Yeah, so what values do we plug into there? It's multiples of pi. Yeah, so thinking about the unit circle, it's this place and this place are the places where sine's 0. And just let me just tell you this too. Later today, I have a class with all math majors. It's a seminar class. And on the first day, I asked them all something they like about math and something they don't like about math. And every single person's thing they didn't like was trig. So like, if you're not loving trig, that's okay. Math majors don't like it either. I never really liked it until I taught it, honestly. But we do have to know how to deal with that. And so sine, and what I'm trying to say is, let me know if you want some help reminding you about trig. But anyway, sine is 0. when x is multiples of pi. So x equals n times pi, where n is a natural number. So 0, 1, 2, dot, 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 dot. And so if we were going to write down the domain of this, it'd be all x values except when x is n times pi. Excuse me. Should we graph this real quick? I'm kind of scared to look at what it looks like. Let's just graph it. I'm curious more than anything. Let's see. Oh, no. Gosh, I hate typing on iPads. Over what? Sine of x. Yeah, so it's like a bunch of weird U things, right? And where are those U things happening? I mean, where's the jumps happening? They're happening at pi values. I see how this, if I kind of screenshot this. Do I want to try this? Let's try it. Yes. Right, all these discontinuities. This right here, this right here, this right here, right? This is at pi, this is at 0 pi, this is at -1 pi. We kind of look down at the other one, right? This is at, so this is 0, 1, this is 2 pi, 3 pi, right? 4 pi, 5 pi. It's all multiples of pi. That's all I'm trying to say here. We have all those discontinuities at multiples of pi. All right. That's all I wanted to say about that. Just give me 1 second. I'm just curious. I want to remind myself really quick about what's in that homework, just to make sure that we covered it all. Continuity. Man, internet is brutal right now. Yeah, so there are some piecewise functions. That's what I was recalling. There's some multiple choice questions. There's some pictures similar to what we just did. So there's a bunch of pictures. That's good. Okay. Yeah, there's a bunch of piecewise functions. All right, we're going to come back to piecewise functions, but I want to look at a little bit about, got just enough time, I think, to look at the intermediate value theorem. There's some questions about continuity. Just say again, I would really encourage you to just check out some of the homework, see which ones look, just familiarize yourself with it basically, because I want to do some in class, but if I do it in class before people look at it, it's usually not helpful. So I'm going to kind of wait for your lead about when to talk about that. We'll probably talk about it at least a little bit on Monday. All right, let's talk about this too, because this is also in the homework next week, and then we will finish off with our short quiz. So the intermediate value theorem is an application of continuity. So I think maybe I'll just note that this is an application of continuity. Yeah. And so the idea is we might care about whether a function hits a certain point or not, but we don't necessarily care what that point is. So for example, to illustrate the concept, I'm going to think about this population of insects. And I just made this one up. Sometimes I use real functions that I pull out of papers, like real scientific papers and stuff. This is not one of those. I just made this one up. But let's pretend that this function right here represents the population of some insect that we care about. And when I talk about this, I sometimes like to think about, well, maybe these are like termites and we're modeling termites inside your house and we care about how many there are because we want to know whether they need an exterminator or something like that, right? Or how many insects are there out in the woods right now for bats to eat? Whatever it is, we care about this population of insects. It turns out that this graph kind of looks like this, by the way. It does like an x squared thing. So that's what P of t looks like. And it gets pretty high. It gets up into the thousands. And let's say we care about whether or not this function hits 5,000. That's sort of the thing we're thinking about. Let's say 5,000 is the magic number where if you have 5,000 termites, we need an exterminator or something like that, right? So that's some number we care about. And we don't necessarily care like when exactly that happens. We just want to know, is that going to happen? Well, there's three options we could think about for knowing if that's going to happen. We could try to set the equation equal to 5,000 and solve for t. And in this particular case, that's something we could actually do because it's not that challenging of a function, right? It's like a pretty easy function. We could use a quadratic formula on that. But in more advanced problems, you might not be able to. So in option number one, potential problems are, or some issues are, doesn't always work. By hand at least, or usually use computers. Or if it doesn't work by hand, it's at least sometimes not easy to do. Again, this is an easy function, but just kind of thinking ahead into more complicated functions might not be easy. Graphing, it's a good way to do it, right? Like if we had the graph that looked right here, if we knew what this top point was, we might be able to say, is it bigger than 5,000? And so that's a good approach, but maybe not exact. And there might be a hidden discontinuity, like a hole or something. Again, in this particular function, it's a polynomial, so we just said that those are continuous, so we're not going to have issues there. But just sort of thinking ahead to more complicated ones, functions can get really weird. I think about that sine of 1 over x thing. If we were trying to like zoom in on a specific part of that really oscillating part, it would be really challenging. And so what I'm suggesting here is we might think about the intermediate value theorem, which is what's being shown on this page. And so that's what we're talking about here. We're looking at the intermediate value theorem and it's being explained right here. And so it's a way we can think about whether a function hits a point without solving an equation, which is option number one, without graphing it if we don't have a calculator or something like that. This is another really nice option. So here's what the intermediate value theorem says. Let's read the math and we'll draw a picture about what it says. So it says, if a function is continuous on some interval, and n is some function value between the output endpoints, then there must be some number between the endpoints such that when you plug the number into the function, you get that middle value. So we'll draw a picture and sort of work this out. But let me clarify a couple of things right off the bat. First of all, this interval AB, these are the x values. And so let's go ahead and just put some x values on the x-axis and label AB. So let's say A is right here and B is right here. And so what we're saying is the function's continuous between those 2 points. And so let's draw a continuous function between those 2 points. And try to make it look something like this, and I'll explain why in a second. In fact, I'm going to move mine over a little bit and explain what you should do. What I'd like to have happen is I want this location, where this hits up here, to be higher than this location. So just make sure that that happens on your picture. It doesn't really matter, but I just don't want them to be even. Okay. right? So we've got this continuous function, right? It's definitely continuous, right? We can trace that function out. It's probably some polynomial, nice and continuous. Keeps going down this way somewhere, okay? Just gonna pause, let folks catch up before we keep dissecting this definition, right? The definition, when you see something like that, I know I've said this before, but it's really just one of the big things in math is just being able to understand the notation and reading that. That's a one sentence, right? It's a one sentence statement. That's really not that complicated. It's not, but without sort of thinking about it and knowing some of the language, quote unquote, the math, it's really confusing, right? Okay, you with me so far? We're gonna keep drawing. So we have some closed interval AB, there it is. We've got a continuous function there. And n is some value between f of a and f of b. So these two things, or these three things, I should say, these are y values. Right, it's the output at points a and b, right, f of a and f of b. And then n is going to be some number between them. So this point right here is f of a. I'm sorry, b. And this point right here is f of a. Right, so this corresponds to this point on the y-axis. This corresponds to that point on the y-axis. And let's pick n somewhere between the two of them is what that says, right? N is a value between f of a and f of b. So I'm just going to put n right here. Let me use a third color. Let's say n is this one right here. And the question is, or what this says, is there some c between a and b that is going to be the output, f of c equals n. Right, so down here then, these are still x values, right? And everything else is defined then. Well, let's let everyone catch up with that picture and then I will say some more. I think I'd like to move this f of a, that's a little confusing. I'm going to move that down over here. Is anyone getting this and want to say it in a different way? Like use different English words to say what we're trying to say? Let me give you an analogy while you're processing this a little bit. If I asked everyone in this room, were you at one point in your life 2 feet tall? You'd probably all say, absolutely. And if I said, when was that? You would say, I have no idea, right? But if I said, how do you know you were 2 feet tall? You'd say, well, when I was born, I was less than 2 feet tall. I'm now bigger than 2 feet tall. I grew between those 2 points. So somewhere in there, I must have been 2 feet tall. This is that same idea, right? If you think about like height growth as a continuous function, you just know you were less than it at one point and you're now bigger than it. And so somewhere in there, you must have hit that point. That's exactly what this is saying. It's saying, if you've got this continuous function between 2 points, one of them is less than the point you care about. Where we care about n, where you want to know if we hit n. N is like 5,000 in the insect example, right? You know 1 point's less than 5,000, or the point you care about. 1 point's bigger than it. It's continuous between there, so it must have hit that point somewhere in between, is what that theorem is saying. Thoughts about that? Clarify that more? So we're not saying anything about when that happens. We're just saying, just like the 2 foot example, you don't know when you're 2 feet. I honestly don't know when it is either. I'm thinking about my daughter's 2, and she's taller than 2 feet, right? She's probably 3 feet now. So sometime between the ages of 1 and 3, you hit 2 feet. But I don't know when it is, and we just know it happened based on this literally just using this theorem, right? So I'm going to write the words down just in case this is not clear. And also sometimes people need to look at this later or aren't here or whatever. So the idea is, since the function is continuous, I abbreviate continuous COTNS. since it's continuous between A, B, and notice how I'm using brackets here, right? Because it's going through those points. That's supposed to be a bracket at least. Since it's continuous on A, B, the function will output all the y values between those 2 points. And when I say those 2 points, I mean f of A and f of B. And so if n is somewhere between those 2 things, it's got to hit it somewhere. So for f of A to reach f of B, I'm just going to say this in a different way in case sometimes people have a real hard time with this and sometimes it's like real easy. So anyway, I'm just trying to reiterate. So for f of A to reach f of B in a continuous way, the continuous part's important, right? You cannot say this unless it's continuous. In a continuous way, we need to pass through all the points between it. And what we're saying is n is in there somewhere. Trying to think about an example where this wouldn't work in some kind of discontinuous way, like I have some stupid examples. I wish I could come up with a better one on the spot. Anyway, when you have like jumps, like sometimes people use the height example, they'll say, oh, well, height maybe isn't completely continuous because maybe at one point you were like a tad bit less than 2 feet and then, I don't know, you like jump over it, like maybe you're not exactly 2 feet. If you have some kind of like jumping thing where you don't get like continuous things happening, you can't use this theorem. Anyway, I'm just trying to point that out because if you have a non-continuous graph, you cannot use this. And the only time you can use this is with a continuous graph and if you quote the fact that it's continuous. That's like a really important part. So we're almost out of time here before the quiz, so I want to drive it home with this example. So let's finish the example we just did a second ago. So we've got this polynomial. In case this isn't clear that this is a polynomial, this is the same thing as this, right? Sometimes people get confused because there's denominators. But they're just fractions, they're like fractional coefficients. So we've got a polynomial, so it's continuous everywhere. If we want to know whether this polynomial hits 5,000, we just have to find a point less than 5,000 and a point bigger than 5,000 and quote the theorem. That's the entire thing. So we start out by saying it's continuous. So since P of t is a polynomial, it is continuous everywhere. And I really can't emphasize this enough. I'm just going to write it in red. This first sentence, I'm going to put this in parentheses. This is not part of the argument. This first sentence allows us to use this theorem. If you don't say you have a continuous function, you cannot use this theorem. This first sentence allows us to use the intermediate value theorem, IVT. So in other words, when I'm grading these problems, I'm looking for you to say, this is a continuous function, therefore we can use this theorem. Really important. It shows me you know what's going on here. Then we just plug some numbers in. And this is an easy thing to plug numbers into. And I just plugged numbers in ahead of class just so we didn't waste time here. And I plugged some numbers in and I found that when you plug 0 in, you get 6, right? Because the zeros, first 2 terms cancel and then you just get 6. And then I just kept plugging bigger and bigger numbers in until I got one bigger than 5,000. And I just happened to plug in 150 and got to 9,006. Since it's continuous, there's one less than 5,000, one bigger than 5,000. It hit 5,000 somewhere between them, right? So since P of 0 is less than 5,000 and P of 150 is bigger than 5,000, by the intermediate value theorem. You're just like quoting the theorem, like you don't have to explain it. It says, hey, look at the theorem, it explains it. By the intermediate value theorem, oops, sorry. There must exist a place between them, and I'll call it a T star, such that T star is between 6 and 150. And when you plug it into the function, you get 5,000. And I love pictures, so I'm going to draw my last picture of the day here. We know this function looks something like this. Starts out at 6. And then somewhere down the line at 150, it's up here at 9,000. So somewhere between those 2 points, it must have hit. Oops, not T star. Oops, not T star, that's 5,000. Oops. Somewhere between them. I don't know what it is, but it has to happen, right? Questions about that concept? Again, this is usually something that sometimes trips people up, and it's not because we don't understand some technique or we don't understand how to solve a problem. It's just it's a notation thing. It's like being able to read a sentence that's written in math.
Could you try to make it smaller to get closer to 5,000?
So if you really cared about the point, then yeah, you might try to like hone in on what point it actually is. But if you just care about whether it's going to happen, it doesn't really matter, right? We just want to find one bigger and one less. Finding the exact number is like another problem, right? That's like solving an equation, and that has its own techniques. Other questions? I don't know if you guys could hear. The question was, should you plug numbers in closer to get it closer to 5,000? And the answer is like, if we just care about whether or not it hits it, it doesn't really matter. Other questions? Okay. So I'd like to use the last 20 minutes class here for this quiz, which again looks very much like the homework and/or class notes, and you're welcome to have that stuff out. I have some people taking it remotely, and so I'm going to share the quiz on the screen here. And so if you're not interested in touching this piece of paper that I'm about to handle, you're welcome to take it that way. But I also can just tell you that I had a COVID test yesterday, and it came back negative. So let me know what you want to do. But again, it looks just like the notes. And if you understand this stuff and you have good notes with you, this is going to be really, really quick. I'm going to go ahead and share it over here, and you can let me know if you want a hard copy. And what I'm going to end up doing is, let's see, I need to plug this in. What I'm going to do is I'm going to put it on Gradescope myself, and I will return it via Gradescope. Okay. This, that. So there it is. Can I get a hard copy? Does anyone not want a hard copy? Stuck on something, I at least show you where to look at the notes, get you started. Remember, the point of this is not to like see you running faster. And you kind of follow along using the notes. So if you have a hard time figuring out where you should be looking in the notes, for example, that's a really good thing to ask. And let's see here, are these guys okay? Oh, that's right, I haven't shared it yet. Sorry, let me share it. Forgot to share.